All right, the second half we've got to go really fast and do a lot of probability problems with a lot of good practice, helping you do homework assignments. I did want to make a couple more comments about this. With this thing from the Bob's gambling, we looked at his average in that game and saw that even though he won a lot at first, he lost money in the long run. I do want to point out that for this particular simulation, the long run average was close to negative 0.4. Where that is, that's close to negative 0.4 if you look at this axis, which is meaning it's close to the theoretical mean, negative 0.4. Negative $40.4, meaning negative 40 cents. That's his long run average. Doesn't always necessarily come out super close, but that one's fairly close. Second comment, and I have mentioned this before, is you'll often hear people call these means expected values. That's a common terminology. In fact, it's more common in advanced statistics to call it expected values instead of a mean. But they do represent the same thing. I think the phrase expected value is a little misleading. You're never going to lose 40 cents on any one play. Okay, so it's not like on any one play you're going to lose 40 cents. Again, that's a long run average. So a couple comments there. All right, into lots of probability. We've talked about the terminology you see here, sample space, event, and probability model. I will just tell you for today that it is on this PowerPoint, but we're going to move on. We also have mentioned probability notation. It's still on this PowerPoint. I have talked about it already today. We'll move on here, and we will use that notation more. I did show you this box before. Now we're going to use it in more depth. Okay? So this is a box of probability rules. These are not the only probability rules. In fact, we'll see one more kind of rule today. These are the most basic. First of all, rule number 1. And you can just write these as equations if you want. The probability of any event is always between 0 and 1. That's our first rule. Okay? Or you could write that in terms of percentages. Though if you do write it in terms of percentages, make sure you put the percent sign. You can also write it's between 0% and 100%. Make sure you put the percent sign. Percent means per 100. So 100% is 100 per 100. 100 over 100, which is 1. That's what percent means. Cent is, an abbreviation for 100. Rule 2. If you're talking about the whole sample space, the probability is 1. In other words, something in the sample space has to happen. Okay? Is essentially what that means. There's got to be some outcome in the sample space that has to happen. In the context of flipping coins, we make the assumption in the model that we always can see what happens. Get a head or a tail. Okay? That, the coin doesn't explode. Some dog doesn't come running through here and eat the coin. All right? The outcomes that we think will happen do happen. That's the assumption that we make. Actually, I did have I had a gorilla come running through my class once, actually. I'm serious. It was in another classroom that had a couple doors, and this guy in a gorilla costume came running through and yelling during my class. Okay? Not that I'm recommending people do that, but that happened to me once. So it was funny, yeah. But it was very unexpected, very strange. I would have said the probability of that happening would have been 0, but it happened. Rule 3, the complement of any event is the event that event does not occur. It's written as A with a C there. That C is not a power. Okay? C is not a number there. It's just notation for the complement. And the complement rule says that the probability that A does not occur is 1 minus the probability that A does occur. Having introduced the complement notation, I don't know why the book didn't bother going ahead and writing that equation like this, with that complement notation in there. Okay? Complement means the opposite, means that A doesn't occur. For example, when I flip a coin, if A is the event that I get heads, then its complement is that I get tails. If I flip a coin 4 times and I count the number of heads, and A represents the event that I get, say, 2 or fewer heads, then its complement is getting more than 2 heads. It's the opposite event. If A is the event that it's raining tomorrow, the probability of A might be 0.2. its complement would be the event that it does not rain tomorrow, and its probability would be 1 minus 0.2, 0.8. It's a very intuitive equation. It's symmetric also. You can solve for the probability of A in terms of its complement, like that. In fact, the complement of the complement is A. The opposite event of A. The opposite of the opposite event of A is A. Rain tomorrow's opposite event is that it doesn't rain tomorrow, and the opposite event of not raining tomorrow is that it does. And also, when you add these probabilities, you have to get 1. These are different ways of thinking about the exact same equation. Rule 4 says that if two events are disjoint, then to find the probability that one or the other occurs, you add their individual probabilities. Disjoint means they have no outcomes in common, so they can never occur simultaneously. For example, an event and its complement cannot occur simultaneously. If it rains tomorrow, it does not rain tomorrow. If it doesn't rain tomorrow, it does not rain tomorrow. Okay? They can't occur at the same time. And we're saying even if it's a little tiny sprinkle, that is rain. Okay? Not a boundary between is that rain or not. We'll see some other disjoint examples in other slides here. But just write this down for the moment. Disjoint means they can't occur simultaneously. They don't have to be complements. Okay? We'll see more examples here. Coin flipping, we've talked about this example before. Flip a coin 4 times and count the number of heads. Call this number x. That's a discrete random variable. What are the possible values? 0, 1, 2, 3, and 4. And there's a probability distribution, a probability model for x, the number of heads. Don't be bothered by the fact that I used k for the number of heads there. I could have used any letter that I want. I'm just thinking of the k's as being different possible values. 0, 1, 2, 3, and 4. This notation means the probability that x equals the different k values is given by those numbers. Over here on this side of the board, I made a graph of the situation before class showing all the possibilities. I went ahead and listed them all in a nice graph, analogous to what your book did in section 4.3 actually. Here's the event that you get all tails. These 4 outcomes are when you get 1 head. These 6 outcomes are when you get 2 heads and 2 tails, of course. These 4 are when you get 3 heads, and this one is when you get 4 heads. The number of heads is 0, 1, 2, 3, or 4, and if you assume each of these outcomes is equally likely, there are 16 of them, and each has a probability of 1/16. Therefore, the probability of getting 0 heads is 1/16, because there's only one of those. The probability of getting 1 heads is 4/16, which is 1/4, or 0.25. The probability of getting 6 heads is 6 out of 16, which is 3/8, or 0.375, etc. If you flip a coin 4 times, your chance of getting heads is about 6%. Excuse me, getting 0 heads is about a 6% chance. That's a probability model for a discrete random variable. Okay, it does satisfy all the properties of probability. The sample space consists of every one of those outcomes together as a set. One of those things has to happen. What are some disjoint events? You could ask, what's the probability of getting 0 heads or 3 heads? If you get 0 heads, you don't get 3 heads. If you get 3 heads, you didn't get 0. Those are disjoint. They can't happen at the same time. So the probability of either getting 0 heads or 3 heads is the sum of these two probabilities. 1/16 plus 4/16, which is 5/16. Catch that? You're going to have problems with this. The probability of getting 0 heads or 3 heads, because those are disjoint, can be found by adding these probabilities. 1/16 plus 4/16 is 5/16, which will be in the decimal 0.3125. Those are disjoint events. You can use that rule, rule number 4. That can be simulated. Here, this gives an indication of how to do so, but again, we don't have time today to go into depth in this. We will next time look at simulations. You should take some time after class to look at the slide and think about why this makes sense, though. Why would this allow us to simulate tossing a coin and counting the number of heads based on this probability model? Here I got some results of a simulation. I got a theoretical distribution. The top one is just a graph, a bar graph of those probabilities. And this is an approximated distribution based on simulation, 160 trials, count the number of heads each time. For example, this bar looks like it has a height of perhaps 0.23. So about 23% of the head times I got one head. Theoretically, it should have been 25%. But because I'm actually doing simulation, it's not going to be necessarily exactly 25%. It's also useful oftentimes to think about probabilities in the context of cards. Standard deck of 52 cards, here's a picture illustrating the different possibilities. We shuffle the deck. We assume it's a well-shuffled deck. And that each of these cards occurs once in the deck. That's the assumptions you make. And you pick a card at random. If it's well-shuffled, I guess you can think of it as picking the top card. But you also, perhaps better, can think of it as picking a card at random. You got the deck sort of spread out. You pick something at random. What's the probability of different outcomes? For example, we could ask, what's the probability that it's going to be diamonds? There's 13 out of 52 diamonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 out of 52. The probability of getting diamonds, which I could denote like this, for short. That's not a very good diamond. Probability of getting diamonds, you could use a D if you wanted instead, is 13 out of 52, which reduces to 1/4, 0.25, which makes good sense. I could ask, what's the probability of getting a face card? Let's just do face card. These are the face cards. How many of them are there? There's 12. 3 times 4. That's going to be 12 out of 52. That can be reduced to 6/26 or 3/13, which is a little smaller than 0.25. A little smaller than the 1 in 4 chance of getting a face card. I could ask, what's the probability of getting a diamond or getting a black card? Notice those are disjoint events. Diamonds are red, they're not black. Blacks are not diamonds. Those are disjoint events. So I can find this probability in two ways. I can either just count those things that are diamonds or blacks, or I could think of it as the probability of diamonds plus the probability of getting a black. Either way you think about it is okay. If you think about it this way, then you would just add the fractions. 13 out of 52 are diamonds, 26 out of 52 are blacks, giving you 39 out of 52 cards that are diamond or black, which does reduce to 3/4. But you also could just count them. 13 diamonds and 26 blacks, 39 total that are diamond or black. Those are disjoint events. They can't occur at the same time. When you pick one card, if you get a diamond, it can't be black. And if you get black, it can't be a diamond. Those are disjoint events. Examples of not disjoint events would be diamond or face card. Because there are cards that are both diamonds and face cards. Those are not disjoint. The probability of getting a diamond or a face card, diamond nicely, diamond or face card is not equal to the sum of the probability of getting a diamond plus the probability of getting a face card. It's not the case, because there are 3 cards that are both. If you added those probabilities, you would be double counting those. So effectively, well, there's 2 ways to do it. There's a formula that I'll talk about next time, but you also can count the total number of diamonds and face cards. 13 here, plus 9 more, giving you 22 out of 52 that are diamond or face, which reduces to 11/26, which is, I don't know, close to 0.4. Am I going too fast? You getting this? You know I am going fast. Okay, drawing pictures like this is supposed to help. It's one tool. Of course, drawing a picture like this by hand would be real painful, but I think cards are familiar enough that you could perhaps think of these things without a picture. But if you want, it's going to be in the PowerPoint. It's always there for you. If you have these kinds of problems. On a test, I guess I'd maybe make a print out of this picture just to help you think through if you need help. Probabilities aren't just for fun and games. They do have applications that are really important in life, or to our country. The government keeps track of labor statistics. And according to the book, in the year 2007, the probability that a randomly chosen adult aged 25 or older was employed was 0.649, or a 64.9% labor force participation rate. It was for people aged 25 or older. In 2015, currently it's down to 62.8% I saw online. That might include people who are like just as young as 18 perhaps, I'm not sure, maybe even younger. There was a higher labor force participation rate in the past. In this case, defined as the percent of people 25 or above who are working. And I think it includes both part-time and full-time. Though maybe with part-time it has to be a certain number of hours, I'm not sure. It's gone down recently, partially because of baby boomers retiring, partially because the economy is, went down in 2008, and the job generation was not high enough for a few years after that to induce a lot of people to participate. There are a lot more people on disability leave as well these days. And the probability that such a randomly chosen adult was unemployed was 2.4%. That's not the same as the official unemployment rate. Does anybody happen to know why? Have a guess? The official unemployment rate was higher than that. I think it was in the ballpark of 4 or 5%.
I'm
You
not
know what?
saying that it's just adults and not like.
That might be part of it.
18.
That's true, that might be part of it, but I'm thinking of something else. There are people who don't work, but are not counted as unemployed because they're not looking for a job. They're not in the labor force, is what economists say. So that's another reason why it's not the same as the official unemployment rate. But yeah, perhaps the age is a factor too. We can ask questions like these. What is the probability that a randomly chosen adult aged 25 or older was either employed or unemployed? No, a person can't be both. At least we say they can't. By definition, you're employed. If you got a job and you're working a certain minimum number of hours. If somebody works maybe just 2 or 3 hours a week, maybe that doesn't count, and they get counted as unemployed. So we're saying they can't be both. Therefore, those probabilities, those events are disjoint. So how would I find the answer? Just add, yeah. Those are disjoint events, they can't occur at the same time. You can add them. You can write your answer like this. The probability that somebody is employed or unemployed, again, because these are just disjoint events, is the probability that somebody's employed plus the probability that somebody's unemployed. So you get 0.649 plus 0.024, and that would be 0.673 for the answer. That's assuming these events are disjoint, which is a reasonable assumption to make. Okay? So there's a real life, important kind of application to be able to think about. Here's some more data related to employment. Question?
Yeah, just on what you wrote on the board, like theoretically, why isn't it 1? Because the, like at the bottom equation on the board there, like
Right.
probability of A plus the
They're
counter.
disjoint events.
Oh.
I'm glad you asked.
Yeah.
They're disjoint events, but they're not complementary because
Okay.
there are people that are not in the labor force.
Okay.
They don't count as unemployed. Good question. Here's more data related to the same thing as well as education. It's good to group this data into a table. So we've got 3 categories for these adults, directly related to your question. Employed, unemployed, employed, and not in the labor force. You're not looking for a job. We also have education level here. X is supposed to be the education level. Less than 12 years means they didn't finish high school. And there are plenty of people who have not finished high school. X equals 12 means they finished high school but no college. X between 12 and 16 means they finished some college. X greater than or equal to 16, that's supposed to be a greater than or equal to, is that they finished college and possibly they've had some grad school. These numbers are, according to the book, taken from the Bureau of Labor Statistics, BLS, and are evidently accurate. These are in thousands, so for example, this is 886,000, not quite a million. This number is 11,521,000, which is really 11.5 million. 1,000 times this would be 11.5 million. Add 3 more zeros, etc. Based on these data, we can talk about different probabilities. Probability, I don't emphasize this enough, is really forward-looking. You're about to do something, like flip a coin or whatever, and you're wondering, you're trying to assess before the fact, what are the chances that something will happen? Okay? Where did I get that probability that a randomly chosen person was employed? I actually took the data from this table. I looked at the fraction of people that were employed at the total. This final total down there, 194,457, which is really 194 million, represented essentially the whole population. What fraction of those people were employed? It was this. So I did that ratio. It's data-based here. It's not theoretical. 126,172 divided by 194,457. Try that in your calculator. I'll do that too. $126,172 divided by 194,457, 64.9%. That's what I had in the previous slide. 6.9, 64.9%. That's your assessment. If you could go back in time to 2007 and you've got everybody who's 25 or above in some big stadium, or not to be bigger than a stadium. I don't know. There are just all these people massed together. Somehow you close your eyes, you pick a person at random. Some crane goes in there and grabs somebody. Are you employed, unemployed, or not in the labor force? I wonder what the chances are. The chances that that person would be employed would be about 64.9%. About 2 out of every 3 almost would be employed. It's your assessment of the chances. We can try to answer other questions. What's the probability that a randomly chosen person is both employed and has finished college but no grad school? Or, no, I meant to say has finished college and perhaps had grad school. In other words, X is greater than or equal to 16. Where'd my shot go? Instead of the word or, I've got the word and here. They're employed and X is greater than or equal to 16, meaning 16 years of schooling or more. They've finished college and possibly have had some grad school. The word and, not or. That word and is just narrowing it down to just this group of people right there. 43,182,000, really about 43 million. Out of 194 million, that would be your probability. It's a smaller probability because not a ton of people have finished college, relatively speaking, and are employed at the same time overall compared to the total. Whatever that turns out to be, that's your assessment of the probability. 43,182 divide by 194,457. About 22.2%. a rule for finding the probability of one thing and another. A couple rules for that, one of which we'll get to here in a few minutes. But for this particular example, you have to look at the data. One other kind of probability we're going to encounter is called a conditional probability. The notation for conditional probability is a little strange, and the idea of conditional probability is a little strange as well. Essentially, when I think about what's called a conditional probability, I narrow down the sample space. I'm going to focus on just people who are employed and ask what is the probability that their years of schooling is 16 or greater if I know they are employed. That's written like this. What is the probability that x is greater than or equal to 16? Again, x means the number of years of schooling completed. If it is given or known that they are employed. The notation for that is to put a vertical line here. Think of that vertical line as shorthand for given that. Given that. Or known that. They are employed. That's called a conditional probability. It's conditioned on the assumption that you know they're employed, is the idea. A conditional probability. Essentially, you're narrowing down your sample space. You're only going to focus on those people that you know are employed, these people. 126 million of them. What fraction of them have completed 16 or more years of school? It's not that divided by that, it's this divided by that. It's a higher percentage because it's a smaller sample space. 43,182 divided by 126,172. About 34.2% instead of 22.2%. Okay, it's called a conditional probability. The idea is that you're looking at a smaller group. We're only looking at people who are known to be employed and asking what percent of them have completed 16 or more years of schooling. And again, this is the notation, the probability that x is greater than or equal to 16. If it is given or known that, that's what the vertical line means, they are employed. It's about 0.342. Okay, so it's winnowing down the sample space. You're going to have a problem like that as well. Last thing to talk about today, here's a slide about conditional probability notation, is something called independent events. And there's a formula for finding the probability that two events both occur when they are independent. Two events A and B are said to be independent or informally unrelated if knowledge that one occurs has no effect on your assessment of the probability that the other occurs, and vice versa. With this conditional probability notation, take a look at this one here. There's a vertical line there, two events. The probability that A occurs if it is given or known that B has occurred is the same as the probability that A occurs. In other words, knowing B has occurred does not affect your assessment of the chances that A occurs. That was not the case for the example I just did. Knowing somebody's employed does affect your assessment of the probability that they have 16 or more years of school. So those two events are not independent. And vice versa, the conditional probability that B occurs, given that it is known that A has occurred, is the same as the probability that B occurred. What's an example of independent events? With cards, getting red, for example, does not affect your assessment of the chances that it's a queen. It's still 1 out of 13. 4 out of 52 cards are queens. 4/52 is 1/13. If you happen to know it's red, or a diamond for that matter, it's still a 1 out of 13 probability that it's a queen. Getting a red or getting a diamond is independent of getting a queen. They're unrelated to each other. In the situation where events are independent, you can find the probability of A and B occurring by multiplying the individual probabilities. Give me another minute here. Don't be putting things away too soon here. You can multiply those probabilities. Okay? Very, very important rule. Quick application of it. Got a problem like this. A series of holiday lights contains 50 lights. The lights are wired in series so that if any light fails, the whole string will go dark. That does sometimes happen with holiday lights. Each light has a probability of 0.01 or 1% failing in a 2-year period. What is the probability that the string of lights will remain bright for 2 years? Okay? Hang with me for about 1 minute. Since the probability of failure for any one light is 1%, the probability of not failing is 99%. 0.99. There's 50 lights. What's the probability that none of them fail? In other words, they all work for a 2-year period. The first one works, and the second one works, and the third one works, and the fourth one works, etc. If you make the assumption that failing or not failing are independent, which is a little bit dubious of an assumption, that they're unrelated to each other, if you make that assumption, you can find the probability that they all do not fail by multiplying the individual probabilities that they don't fail, which are all 0.99. Since there's 50 of them, you've got to raise this to the 50th power to multiply 0.99 times itself 50 times. The probability that they all do not fail, they all are still good after 2 years, is 0.605. I used the rule, an extended form of it for 50 terms. For independent events, they're to calculate that. Okay, if that went by too fast, watch the end of the video. See you next week.